Hey, this is Mr. Beckstrom, and today we're going to do an example from section 5.2. This is one-to-one functions and inverse functions. So a quick review of a one-to-one function is that a one-to-one function is a function that also passes the horizontal line test. Let's just go through a couple of quick visual examples. So we've all been working with parabolas, so let's say we have a parabola. We know that a parabola is a function, therefore it passes the vertical line test. That means that no matter where we put a vertical line, it's going to go through at most one point on the curve. It can never go through more than two or more points. If we can find any place that it goes through two or more points, then it's not a function. Now a one-to-one function is a curve once again, and this time it has the additional restriction that it passes the horizontal line test as well. And the horizontal line test says that no matter where we draw a horizontal or a vertical line, we can never find a place that it goes through two or more points. Notice this first graph here. If I put a horizontal line right there, it goes through the point right here and right here. So parabolas are not one-to-one functions. But something like this might be a cubic function. That's a polynomial, third-degree polynomial, or some odd type of polynomial. They generally do pass the horizontal line test. So this is they're both functions, but this one is not one-to-one because we can find a place that it goes through two or more points, the horizontal line, and this one is a function because no matter where we put this horizontal line, it goes through at most one point on the graph. Notice this horizontal line goes through this one goes through that one. All right, so now that we have a quick kind of visual idea of what a one-to-one function is, we have some really nice properties with them, and one of them is that we can find their inverse if the function is one-to-one. And finding its inverse we have some really nice things about it, and we know the range and the domain of the inverse function because they're just the reverse of our normal function, and we'll see how here. So the question says we're given this function here. Find its inverse and check your answer, and find the domain and the range of both the original function and the inverse. So since we know it's one-to-one, we know we can find its inverse, and to find an inverse we take the original function, which is y is equal to 5 over 2 plus x, and one method to find it is just to replace x and y with each other and then solve for y. So if I do that, I'm going to get x is equal to 5 over 2 plus y, and now I want to solve for y. So one thing I'm going to do is when we have an equation like this, I can flip both sides. So I'm going to do 1 over x is equal to 2 plus y over 5. That's a nice property you may not have seen before. And the reason I did that is now I can multiply both sides by 5. So I'm going to get 5 over x is equal to, the 5's cancel out over here, 2 plus y. And then finally I subtract 2 from both sides, and I've reverse it around. I'm going to get y is equal to 5 over x minus 2. So this here is my inverse function. This is my normal function. This is my inverse function. So the domain of this function, since it's one-to-one, is going to be the range of this function. And the range of this function is going to be the domain of this function. So let's go ahead and check this out. So it says find the domain and the range of both of these functions. So I'm going to do let's call this one, well, this is function f. So the domain of that, domain probably figure out a better way to write that, but that's okay, is going to be what? It looks like every value except for -2. Why? Because -2 makes this denominator equal to 0, and we can't have a 0 in a denominator where the function is undefined. So I'm going to write it in set notation, x such that x is not equal to -2. All right. So this is my domain of my f function. Now, the next thing I want to find is the domain of my inverse function that I found. And I'll show you why I do it in this order in just a minute. So if I do that, it looks like I can have x be anything except for 0. Because if x is 0, then I get a 0 in the denominator here, and the function is not defined. So in this domain here, it's going to be x such that x is not equal to 0. Now, prior to this, when we've looked at the range of functions, one of our best ways to do that was to go ahead and graph it and just kind of take a look at it and see, for which values we had y's. But since we know the inverse exists because this function is 1 to 1, we know that the range of this function, is simply going to be the domain of this function. So this is going to be y such that y is not equal to -2, and the range of this function here is simply going to be basically the domain of this function here. So this is going to be y such that y is not equal to 0. All right. And that's pretty much it. So in this case, I don't even really have to look at a graph. Now, if I wanted to check my answer, I could go to my graph, put this in my y equals just to make sure that that looked like it made sense. I should have vertical asymptote x equals -2 for the f function, and it should go through pretty much every value except for 0. And then for the inverse function, I should have a vertical asymptote at x equals 0, and it should go through every y value except for -2. All right, if you have any questions, let me know, and I hope you have a great rest of your week. Thanks.